Zombie Apocalypse.
Okay, good day everyone. So actually this is my report to my dearest professor in Advanced Physics 2, Modern Physics, under the supervision of Dr. Dante Garrido, under the Master of Engineering Science program of University of the East Manila. So my topic for today is applications of relativistic mass and energy. Kumbaga ito na po yung magiging showcase ko dun sa diniscuss kong concepts and principles regarding the relativistic mass and energy that is actually popularly known as that E is equal to mc squared. But I would like to expound more the use of this formula and its attribute of what we call relativistic mass, relativistic time, or what you call time dilation, and relativistic length or length contraction. So be ready to be neurorized. Okay, for the first problem that we're going to solve will be taken from, actually the three problems will be taken from the author survey and Jewett. So title of the reference book is Physics for Scientists and Engineers with Modern Physics, which is the 9th edition. Okay, now let me proceed to the very first problem under page 1220 of that particular reference. So let me start first with this very good example, example 39.10, mass change in radioactive decay. So here is the problem. Okay, there is actually an element polonium, okay, with a mass number of 216, or also known as, actually it is the sum of the proton and neutrons in the nucleus. So the mass number 216 of polonium, whose nucleus is unstable and exhibits radioactivity, okay, as depicted by the chapter 44 of that particular reference book. It decays to a lead or plumbum of mass number 212 by emitting an alpha particle, which is an helium nucleus, which is mass number 4. So the relevant masses in atomic mass units, so I will show you the table later, that the initial mass, no, that is equivalent to polonium of mass number 216, no, equals 216.001915 of U, whereas U is actually a unit of mass. And finally, the mass of the final condition is equal to the mass of the lead or plumbum, which is mass number 212, and plus the mass of the helium with the mass number 4 is equated to 211.991898 of U plus 4.002603 of U. Now we have two figures to solve. Find first the mass change of the system in the decay, and of course find the energy that this mass change represents. Okay, so let's start. How do we configure the solution? Okay, let's take a look on what does the table A.1 says here in Appendix A. Now, taken from the book, it is mentioned, no, that one atomic mass unit in kilogram is given as 1.66 times 10 to the negative 27 in kilogram. Now, our main interest, let's say in terms of mass, okay, let's try to interpret it as in terms of kilogram, whereas that's equivalent to 1 times U, or simply a value of U. Okay? Then we are going to use that later. So let us focus on the question letter A, find the mass change of the system in this decay. Now notice that the polonium under unstable condition, which is actually your initial mass in concern, no, equals to 260.09115 U, and the final mass under the actual condition, which is providing us a value of, in terms of this, is actually the potential decay is present. So therefore, taking their differences will be the mass change or the delta value or the change in mass. So by this, so for conceptualization, the initial system is the polonium with a mass number 216 nucleus. So you have to imagine that the mass of the system is actually decreasing during the decay. Of course, when decay is our main topic, it should so be decreasing. And the transformation to a kinetic energy of the alpha particle, and as well as the plumbum or the lead under the mass number 212 after the decay. So therefore, as we progress with the calculation. So categorization should be, we use concepts discussed in this section. The section that is pertaining to the relativistic mass and energy. So we can categorize in this example as a substitute problem, like this. So there's a need for us to calculate the change in mass using the mass values given in the problem statement. So therefore, the delta mass, delta M, is equated to mass initial, no, minus the mass of final to denote that there is a decay happening. Of course, delta mass is already in terms of negative since to depict that this is decay. So if you want to take the real sign, then take the mass final minus mass initial. Now, taking this algebraic difference, no, the mass initial and the mass final phrase, you will get that their change in mass is 0.007414 of U. So, positive siya kasi in-inject na natin na yung delta M naught is already negative outside the phrase. So, we accept that is already decaying. So, therefore, by that sense, then applying U as 1.6607 times 10 to the negative 27, no? I-apply nyo lang po yan. Sabihin, 0.007414 times 1.66 times 10 to the negative 27. And then you will arrive that the mass of decay is for about 1.23 times 10 to the negative 29 kilogram. So that would best fit the question as an answer to letter A. Then how about the next question? The next question suggests the question like, what is now the energy upon this mass change, no? Upon the decay. So therefore, in that solution, using the equation 39.24 to find the energy associated with the mass change. So, ano ba muna equation 39.24 by that particular book of survey? This is very popular, no? That the equation 39.24 is actually related to the energy, the rest energy of the particle. So given that E is equal to mc squared, but we talk about changes of the energy, so therefore M will now represent delta M as the decay mass. So therefore the rest energy is equal to delta mc squared, where c is the speed of light. And the speed of light is under the vacuum in all inertial frames, meaning it is isogonal in nature, so it does not vary with respect to other spectra under vacuum. Is said to be 3.00 times 10 to the 8 meters per second. Okay? So, yan pa po yung unit ng speed of light under vacuum, isogonal condition. And then, of course, the mass of decay earlier is 1.23 times 10 to the negative 29 kilogram. And then, as an energy, as a work done, then we provide 1.11 times 10 to the negative 12 joules. Now, but in conversion, in 1 mega electron volt is equal to 1.602 times 10 to the negative 13 of a joule. So if we want to get the equivalent mega electron volt, so therefore we divide 1.11 times 10 to the negative 12 by the value of 1.602 times 10 to the negative 13 of joule, since that is 1 mega electron volt. And then therefore we can now get 6.92 mega electron volt. So that is the answer on letter B. So as a summary, sa mass of decay is about 1.23 times 10 to the negative 29, and for the energy under this decay condition is 6.92 mega electron volt. Usually, the energy under this condition of rest, no, is most likely interpreted as an electron volt or mega electron volt. Okay, to depict that this is under relativistic condition, relativistic energy and mass. So that's the answer. Those are the answers for the first problem of this presentation. Now let's proceed with a deeper problem that we might want to consider. when there are some, a source of derivation to depict how does the equation under relativistic problems are being maneuvered. So let's take a closer look onto the next problem. Problem number 2 relates to page number 1229 of that particular book, and here is the question. Under problem 58, no, you have to show that the energy momentum relationship in equation 39.27, that is E squared is equal to P squared C squared plus MC squared quantity raised to 2 follows from the expression of, from the rest energy equation, that is total energy is equal to gamma MC squared, and then of course for the relativistic linear momentum P is the gamma mu. So whereas the M represents the mass, U represents the velocity of the moving observer, it can be also the velocity under the stationary observer dependent on the application, but let us try to depict under possibly a moving observer. Of course, dynamically speaking, as a work done is being illustrated, and it may be considering, no, a rest energy of the particle, or maybe if we were to take the sum of all is the total energy. Okay, so usually it is the total energy that will prevail under this gamma influence. Okay, so under the concept of total energy, okay, total energy is equal to gamma mc squared, kasi yung concept of rest energy E is equal to mc squared is just only applicable to stationary particle. But if this moving, so there is what you call a summary of a summation of energies. That's why we introduce the value of gamma, where gamma represents the factor of simultaneity for time, or what we call the time dilation. Also, it can be representing the length contraction because they occur they occur at the same time. No, length contraction or relativistic length. And also, don't forget that it is also for relativistic mass. Don't forget the title for this session is relativistic mass and energy. So therefore, we need to get and idealize the total mass. No? So, and of course, the P represents, as I mentioned earlier, relativistic linear momentum. And the mass, of course, M, and then U as the velocity of the moving observer. Now, what we can do is this. No? We can try to square this equation, no? Both of them. And then, observing what will happen, then you will see this. So therefore, after squaring both of the equation here, okay, what should be next? Let's try to choose the multiplication of the second equation by c squared and subtract it from the first. So meaning, we need to multiply the second equation by c. So you have to multiply it by c, okay, be c squared, or the square of the speed of light, okay, so that they have commonalities of unit. So then, after that, we can take it as per difference, okay? So, let's say this is the first, and this is the second equation. So, therefore, we will get E is equal to, okay, E squared minus P squared C squared equals the square of the gamma MC squared minus square of gamma mu squared quantity C squared, okay? So, it is a simple algebraic equation to follow. So, what's next after that? We can obviously see that gamma square is easy to factor out. No? It is common to gamma square. Then, this would be the final phase. No? But don't forget that gamma also has a value. Okay? So, after rearranging this phrase, internal phrases here, mc squared raised to 2 can be also factored out. Kasi here, we can factor out is mc squared raised to 2, and the other side is just purely m, okay, m squared, no, c squared, u squared. So by this, so there will be some allocation of multiplying c squared over c squared so that we can safely factor out mc squared. So therefore, what will be left inside the phrase is 1 minus u squared over c squared. So a simple derivation technique from algebra. So don't forget that the factor for relativistic time, length, and mass, and also kasi simultaneity, has a value. Now, it is actually based on Lorentz application, Lorentz derivation. No? So, what is the value of of that particular factor gamma? We substitute the definition of gamma now. Don't forget that gamma is just only the value of a unity over the square of 1 minus u squared over c squared. So therefore, in a more depictive equation, it can be said that it is quantity of 1 minus u squared over c squared. All are raised to negative 1/2. Okay? So then, as we supply that value of 1 minus u over c squared raised to negative 1/2 in terms of an existing gamma as raised to 2 in the equation in the latter equation that I have discussed. So that would be canceling out the full constant 2. 2 over 2 is 1. So therefore, that will yield to a raised to negative 1. Now, it's easy to understand that when we try to multiply, okay, notice that, let's say the 1 minus, okay, u squared over c squared, and of course, that value, let's say, is let's say value of x. So, x there, okay. So, x raised to negative 1 times x, okay, is just simply saying x over x or equals 1. So, therefore, that would cancel out both phrases. So, all in all, that would have become e squared minus p squared c squared is equal to mc squared raised to 2. Now, is that your final answer? Yes. Now, as depicted, as we try to extract on the other side, that would be the same as e squared is equal to p squared c squared plus mc squared raised to 2. So those are the relationship of the rest energy, no, as in terms of a total, no, total energy. So this would be the relation of total energy, relativistic linear momentum, the speed of light, and the mass of a particular particle. Okay? So that's what we can call coerat demonstratum. So we have proven that that equation really exists. So that is for problem number 2, as found on page 1229 under problem 39.58. Now let's move on to the last problem when we are going to try other parameters that can be connected to this specific kind of situation for relativistic mass and energy to showcase the concept discussed in one of my video lecture, okay, or video presentation dedicated under the supervision of Dr. Dante Garrido for our course Modern Physics or Advanced Physics 2. So let's take a look on to the last problem, the third problem. Same page, problem number 3, page 1229. Now, let's take a closer look on this problem. This is actually one of the, I think, most interesting part of this presentation. Now, the rest energy, or E, no, of an electron is said to be 0.511, 0.511 mega electron volt. So the rest energy of a proton is 930 mega electron volt. Assuming that both particles have kinetic energies of 2.00 mega electron volt, we have to find the following. Letter A. What is the speed of the electron? Letter B? What is the speed of the proton? Letter C. By what particular factor does the speed of the electron exceed that of the proton? Meaning we are to undertake the ratio of both. And letter D. What if we repeat the calculations in part of A to C, but assuming that the new particle condition has a kinetic energies like 2000 mega electron volt. So jumping from 2 into 2000 mega electron volt, let's take a closer look. Does it have an effect to the speed of those respective particles like electron, the proton, and their particular aspect ratio? So let's take a closer look on how do we solve this kind of problem. Okay. This is already derived from the condition of relativistic kinetic energy. And this is already done by my classmate in the grad school of the same course. Okay. So let me use the derived condition. No? Because the topic of mine is just related to best energy, and I have to take a closer look of those derived equation already. So if you want to see this derivation, kindly check the presentation of my group mate. So for that particular topic, relativistic linear momentum, okay, and relativistic kinetic energy. Now, from that equation that K is equal to, or K represents the relativistic kinetic energy, equals the factor for relativistic time, length, and mass minus 1, quantity mc squared. So whereas gamma can be best represented by 1 over the square root of 1 minus u squared over c squared minus 1 close quantity mc squared, then we have this following phrase. So what we have done here is we try to get the common denominator, okay, and then try to extract inside mc squared, and then we try to simplify this by transposing this minus mc squared, no, okay, into the left side. That's why we got k over mc squared plus 1. In the other way, no, it's up to you. So it can be done like k divided by mc squared, no, and then plus 1 as a transposition equals the factor gamma, okay, the gamma unit. And then further simplification can, of course, finding the common denominator. So mc squared over mc squared there, then we finally get this k plus mc squared over mc squared. What is our main idea of doing this? We try to concentrate onto these two relation. Okay? These two relation there. Our main objective is to get an equation phrase, no, for the speed or the velocity of a particular particle in terms of the relation to the relativistic kinetic energy that is already given as 0.5111 mega electron volt for electron and 938 mega electron volt for proton. Okay? And of course, kinetic energies for 2 mega electron volt. Okay? So those are the needed relations. So by this, you can have this relation by taking the reciprocal and then trying to square. So then you will get this meaningful equation, no? Raised to 2. And then a little bit manipulation from algebra. So eliminating the plus sign and the negative sign here. So parang ang nangyari po is ililipat natin dito sa kabila and also the other way. Okay? And then you will have this wonderful equation, u squared over c squared equals 1 minus the quantity mc squared raised to 2 over the quantity of k plus mc squared raised to 2. That will become like this. So after multiplying it by, of course, c squared, algebra manipulation again, then, of course, taking the square root, I mean, so to eliminate the square property of that particular velocity u, then you will get this. So this will be the equation that we're going to use. U is equal to c times the square root of quantity 1 minus close open quantity mc squared over k plus mc squared, that is raised to 2 alone. So that will be our equation to be used to analyze question letter A, B, and C, as well as letter D. So let's take a closer look on how do we apply this equation. Okay, let us take a closer look of this. No? What are given here is the rest energy of an electron volt. The mass are not given. Okay? But, of course, if you will review the equation again, okay, E is equal to mc squared, right? So therefore, I can say that U can be also interpreted as a function of rest energy equals C quantity 1 minus quantity E over K plus E, okay, raised to 2, and all are, that particular phrase is raised to 1 up, or just take the square root. Okay? So applying that, we learned that from this given that the rest energy of the electron is 0.511 mega electron volt, and the kinetic energies for that particular aspect is 2 mega electron volt. So 2 plus 0.511, we will get 2.511, and then of course E as 0.511, applying, of course, as a function of the speed of light, then we will get that electron has a speed of 0.979 c, meaning it is 97.9% of the speed of light is the actual velocity from the rest condition to produce that particular kinetic energy of 2 mega electron volt. Now, let's proceed with the proton. Okay, this time the proton is applying 938 mega electron volt. Okay, that's your E. And the K plus E is 938 plus 0.511 mega electron volt. So roughly estimated as around 940 as depicted here. Okay, so therefore we can now have 0.0652 of C. So meaning 6.52% of the speed of light is the actual velocity of travel for that particular proton in the same condition, relativistically viewed. And to entertain letter C, the action of the factor speed of electron with respect to the speed of proton or the velocity. So we take the ratios, U of electron or speed of velocity of the electron over the velocity of the proton. So we try to divide. Then we will have an aspect ratio of 15. In the set value, we will have about 15.0153. Okay, that's the value, no? 15.0153 as a ratio. But most likely tolerable for having a relativistic condition, since we are taking a closer look of how many times does the electron, okay, takes the speed compared to the proton. So therefore, as a comparison, as a point of view, so under this case, electron is moving relativistically because 15 times of the speed is, a huge factor. So it is visibly understandable that it can be easily viewed. If we are going to have, one of them are considered as the moving observer, and one is what we call the observer under stationary. So both of them is either one of the two. They can see each other that they are really fast moving. So again, but the classical expression of 1/2 mv squared, actually is already familiar to us using dynamics of motion. So therefore, is accurate to 2 digits for the proton. So what's the claim about this? So if we will try to take a closer look, if we will take the velocity squared times the mass of that particular condition, well, you can get the mass and then you can get the 1/2. You will notice that the accuracy is most likely the same as 15.02. Okay? But after that specific data, no, that 5.3 can now change. It may be the same point 15.01, or I think I suppose I calculated it as 15.0285, no? So therefore, there is a variation after the 2 digits for the proton. So therefore, that's the case sensitivity of letter C. Pero how about if we consider 2,000 mega electron volt, what will happen? Okay? What if K is really large enough to be understood and calculated? Let's take a closer look of what will happen. So as a conclusion for A, B, and C, if your kinetic energy is 2 mega electron volt, then it is relativistically really moving. Okay? It can be easily to be seen that they are really fast moving. Okay? Now doing for electron under the condition of 2000 mega electron volt. So we will get this, no? Then that is already 0.9999997 C, or almost 1 times of the C. But let's take a close look for accuracy, okay? So I'll take all of this until it does not become 9. Now, for proton, that is 2000 plus 938 mega electron volt. So you will get 2938. Then you will get 0.948 of C. Now let's compare. These two seems to be different. It is, there is some issue of similarity in electron. However, in proton, it is huge in difference from 6%, 6.52% into 94.8% of C, meaning there is a large gap of changes as you increase the relativistic energy. So therefore, there can be possibly a case where if you increase possibly the relativistic energy of that particular particle, it seems that the ratio of both electron and proton, as you will take it, is almost tolerable. Let's take a closer look. You will notice that when you divide the velocity of electron and the proton, it turns out to be 1.06. So let us try to compare from a small charge into a large charge of kinetic energy. Then it is, almost similar. From 15, a large gap, okay, into 1.06, almost similar, almost same value. So therefore, we can conclude now that as the kinetic energies of both particles become large, their speeds approach c, almost the speed of light. And in contrast, classically, the speed would become large without any finite limit. Meaning, without a boundary, we can say that in the classical dynamics that we are often computing, no, the kinetic energy, it would become large without that particular boundary. So that is the meaning of this third problem, as we observe that as we increase the kinetic energies, it has a particular effect. So the larger the value of the kinetic energy with respect to the electron and proton, it seems that it is almost equal to the vacuum velocity or the speed of light under vacuum condition in all inertial frames. So that is the definition of problem number 3. So for that, the references of solving this problem are the following. Okay. So thank you for viewing. I hope that you have learned from my discussion for today, showing the relativistic mass and energy problems related to this. And kindly please subscribe to my YT channel. Don't forget to hit the like and share button below. As a tradition, you have been memorized, and thank you for viewing. I hope to see you in our next video lectures. Okay? Thank you very much.